Let me just remind you on some notation that you've already learned, okay, in the history of math. When I draw this, here's my question to you. What does that mean? What does that mean? So somebody tell me what that. What this means is x can be anything greater than 3. We just had the quick discussion that when it's an open circle, it does not officially include the number 3. Right? When it's a closed-in circle, it does include 3. Yes. Okay? That makes a distinction when we talk about our notation. Do you remember when we did interval notation the other day that open parenthesis meant it doesn't get to that value? Like when we talked about negative infinity, we could never reach negative infinity. We can only get closer and closer to it. Okay? And brackets, meaning that we actually get to that number. Okay? This notation, if we were writing interval notation for this, we would actually have to write 3 to infinity with this graph as interval notation. Okay? There's no domain and range on this. This one's just one value. It's just an x. But the interval notation would mean that this goes from 3 all the way to infinity. Okay? Parenthesis on 3, because it doesn't actually get to 3, it just gets really, really ridiculously close to 3. Okay. So for instance, this number, the numbers that are okay to be on this graph, that are represented by this graph, are like 3.1. You can write a smaller number than that, 3.01, 3.0001, 3.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 Okay? Okay. So this notation, a parenthesis when you can't get to the value, when you actually don't get to the value, a bracket when you actually get to the value. Okay. That's what we're going to talk about. So you guys have your notes in front of you, which is this, right? Let's talk about this. Here's the distinction on this first graph that we're looking at. Is this graph connected? No. No. So we don't use our interval notation for it, right? We don't use all that fancy stuff. All we do, since it's just specific little points here and there, all we do, we just write the values that they can be, that x can be for our domain. We just write them down. We don't do anything fancy to it. Okay. All we do is we just crank this out. What's one value for x under the domain? That's our x's, right? -4 for this point. -1 for that point. 1 for that point. And 4 for this point. Right? That's all we do. When it's not connected, we just write out the things because interval notation implies that the graph's connected in between those two numbers we write. For range, what's the furthest down? For that point, -1. For the next point, right there, 2. For the next point, 4. And for that point, 6. Yes, it needs to be least to greatest. Yep. Mm-hmm. Although if you did greatest to least, I'd probably let it go as long as it's in a specific order. What we're going to focus on today is we're going to focus on more specific versions of notation. There's 3 different types of notation we can use on these graphs. Okay. Let's backtrack. What have we done this chapter so far? We graphed points on a coordinate grid. Okay. We talked about relations in general. We talked about what it means to be a function and what it means to not be a function. Okay. We evaluated functions when we had the equations. Okay. Those are all things that we did. We looked at pictures, we looked at graphs, and we got information from those graphs, and we made conclusions based on those. Okay. That's all of the stuff we've done so far this unit. Okay. Today what we're going to do, we're going to do a more specific look at, we're going to take a more specific look at notation and the different types of notation that you could see in terms of what a domain is and what a range is. Ultimately, why do we need to deal with domain and range? Well, it's just a statement, it's a description of what the graph or what the problem is, okay, or the relation is. It's a different version of describing the relation. Okay, so we're teaching you yet another way to describe the same exact thing, which is a very similar thing that you keep doing in your English classes. You talk about English structure. Well, notation in math is kind of like the structure of English. You talk about like writing poetry versus writing a persuasive essay. Like those are two totally different representations of the same types of things. Okay? What we're doing with the different notation, doing domains, it's different descriptions of the same type of thing. Okay? Again, domain and range, one description of what a function is or a relation is. Okay? A graph, another description of what a function or a relation is. A mapping, another description of what a relation or a function is. These are just different ways to represent the same stuff. You do that in everything we do in school and in your life. You try to represent things in different ways so that we understand them more fully and more thoroughly. So in math, domain, and range, we're trying to understand a little bit more thoroughly by focusing on a specific type of description. That was a lot of words. Okay, here we go. We're going to do interval notation on this. If you notice this graph, we did interval notation already, and that's what we're familiar with so far. So we're going to start talking about it that way, and then we're going to go into the algebraic and into the set notation. Okay. If you remember when we did domain, we either made a decision between a parenthesis or a bracket, and the two questions we asked for domain was how far to the left does it go and how far to the right does it go. Okay. And then we turned around, we made a decision whether it was a parenthesis or a bracket again. We did the same exact thing pretty much for the range. We did the same decisions based on the notation there, but we asked ourselves how far down, and then we asked ourselves how far up. That's just a summary of the notation that we did and how we did it. Okay? So let's go ahead and interval notation. Get the interval notation for this down. So our first question is how far to the left for the domain? How far to the left for the domain? It's an arrow, and you keep traveling to the left forever. Since we travel forever, it's negative infinity. You cannot ever get to infinity, so we have a parenthesis rather than a bracket. Okay. This very same thing is true for when we ask our question, how far to the right? Okay, we're going to the right forever. We're going to the right forever, so we do a parenthesis and and infinity. Parenthesis instead of bracket because we can never get to infinity. We just go closer to it. Okay. Range on this, we go down forever and we go up forever. Down forever, up forever. That's negative infinity to positive infinity. Okay? When we change this into algebraic notation, we change the way we ask the question about the domain. We change our question to what values of x can it be? And I know the English on that, the structure is probably not very great. But what values of x can it be? In this picture, what are the values? That's the question I want to pose to you right now for you to answer. What values of x can this graph actually be? This graph is connected. It goes everywhere to the left forever. It's connected all the way through the middle and goes everywhere to the right forever. Okay. To express that algebraically, we give this fancy R. That fancy R represents all of the numbers, all real numbers, all of them. Okay, that's what that notation means. For the range, how far down does this graph go? Forever. And it's connected all the way up and it never breaks and it keeps going up forever. We can be all of the values for. So what values of y can it be? Okay, we're connected all the way up to this guy forever. When my 3-year-old son wants to represent something that's really big, it's like all the way up to the ceiling, up way up high to the ceiling. To the ceiling is really high for him. Like that's like the limit of where his concept of large thing. To this all the way up to this, I want pancake to the ceiling. It's true. It's cute. Anyways.
Sounds like your kid.
All right, set notation. It's a little bit more specific than algebraic notation. Essentially, we take algebraic notation and we give it a little bit more of a formal twist. Okay, we do this curly bracket, this squiggly bracket, which is hard for some of us. But that's okay. Do your best to draw a squiggly bracket. Yep. A number x, what we're saying a value x, a variable x, because we're talking about domain. This line right here means such that. Okay? It's just fancy notation. We'll get used to it. The squiggly bracket is just opening the set. The x means, okay, we're defining a variable. We're saying our variable is x for this one. The up and down line math means such that. So a variable x such that x can equal all of the numbers, which is the big R. And then we close our set with the squiggly bracket. For the range, we do the same thing. Open the set for a variable y such that y can equal any number in the world. Okay? Just the formal notation. Pretty much what you wind up doing is you take this statement right here and you write it right there. Notice how those are virtually the same thing? Okay, you're going to see that more as we go on. All right, let's do the next one. On this graph, we have an equation here. So we know that it actually is connected and it goes on forever because it's an equation for us. So the picture should actually look like that with arrows at the end. Let's go to interval notation. Remember our questions, bracket or parenthesis, and how far to the left? Does it go forever to the left? Yes. It's parenthesis, not a bracket. Forever to the right? Yes. Don't know. Okay. Interval notation, again, range. The furthest down that this graph goes is what value? 0. It gets to 0, though, right? It hits it. So it's a bracket because we actually hit it. And we're going up forever. All right, let's then go to algebraic notation. Algebraic notation. Domain, we said it was all the numbers, right? Because negative infinity to positive infinity means all the numbers. Algebraic notation for the range is going to be a little bit different. Remember, the question is, what values of x can we be? Are we allowed to be? We said that it was 0 and up, right? That's what the closed bracket at 0 means to infinity. We're saying that it's 0 and up. If it's 0 and up, we're everything greater than or equal to 0. And range is y, so we write y is greater than or equal to 0. Okay? Now we're going to change it into set notation from the algebraic. In domain, we use a variable x. So we're opening the set. We're saying variable x such that x can be anything. The fancy R. Okay? That's what that means. Yes. Okay, go. Yes. For algebraic notation or for set notation for this one, for the range, we do open the set. We're saying our variable is y such that y is greater than or equal to 0 and the parentheses. Notice how it's the same kind of thing? Except we have the fancy brackets. We have y again with the line. That's the only change from that one. Okay? All right, let's do the next problem. This one, just to clarify, it starts at 0, 0, and it goes that way, like that. Okay, and I know that because there's an equation written by, so I know it actually keeps going forever. So why don't you guys write this out, the domain and range? Okay, go. I would start, all right, interval notation. I'm going to start there because that's where we started. On the picture, it starts at 0 to the left. Is the furthest to the left is 0. It goes to the right forever and ever. Range. Furthest down it goes is 0. It's a bracket because it got there. It goes up forever and ever. From that, I'm going to look at algebraic notation. That goes from 0 and greater, everything greater than 0. So it's x is greater than or equal to 0, because it's 0 and more. Algebraic notation for range is y greater than or equal to 0. What values can y actually be? What values can x actually be? Okay. Then I'm going to turn it into the set. Open the set for the variable x such that x is greater than or equal to y. Greater than or equal to 0. Sorry, I misspoke. Then for our range, we had y is greater than or equal to 0, but we need to say, okay, our variable is actually y. And with the squiggly brackets. Look at another one. Did you guys get that down? Sorry, I pulled it off too fast. And this graph looks like so. If I were to trace it better. Start at interval notation. The furthest to the left is infinity. It goes forever to the left. It goes forever to the right, and it's connected all the way in between, so we can draw that. For the range, the furthest down it goes, and it actually gets to the value 0, and it goes up forever. Algebraic notation, if it's negative infinity to infinity, it's all of the values to the left, all the values to the right, everything in between. Range goes from 0 and up. So it's y is greater than or equal to 0, because it's 0 and then everything greater than that, including 0 because there's not an open circle to dot. Set builder notation x such that x is equal to the range, or equal to all real numbers. Means it's all of them. This one, variable y such that y is greater than or equal to 0. Let's go to the next one. Next one's a little weird. Notice how this one kind of creeps down here, and it kind of pans out. This one actually never gets to 0. When it looks like it's creeping really close and kind of evening out 100%, we can often say that it doesn't actually get to 0. I know for sure because it's an exponential function, because I know more about exponential functions, but for us right now, just know that it's not getting to 0, it's just creeping to it. Interval notation. The furthest to the left this picture goes is forever. Furthest to the right, forever. It creeps slowly, but it still is going. Range, furthest down is actually 0, but it doesn't ever get to 0. It just gets really close. So it's a parenthesis, which says it's getting just close. Yes, sir? Why is there a parenthesis rather than a bracket on the 0? Great question. It's because earlier I had mentioned that this didn't get to 0. Okay, so it's a parenthesis because it doesn't officially get to 0. Why doesn't it get to 0? That's a longer answer. Okay, and it goes up forever. Would it be like okay, algebraic notation. Algebraic notation is all reals for the domain, and for the range, it was everything greater than 0, not including 0 in this. We don't do the underline. Set notation. X such that x is equal to the range. The range for set notation is going to be y such that y is greater than 0, not the underlined part because we never got to 0. Okay? Let's keep going. One more set of stuff that we're going to talk about before we leave, okay? You guys are doing a great job today. Some good questions being asked. Keep coming at me if you don't understand it, of course. Never just sit there in your own self, I don't understand it. Just keep coming at me. You keep coming at me. You keep coming at me until you get it. Okay. It's my job to help you get it. It's your job to keep asking me how to do it and how to get it. Okay? All right, on this question, remember when we evaluated these f of things? Okay, what was inside the parentheses? What is actually inside the parentheses? What's in the parentheses when we do this notation? That's what we plug into the equation, which is what we previously did. We put it into an equation for x. We don't have an equation on this problem, do we? That's a problem. We have a different representation of what this machine f is doing. This relation f is doing. Okay? But we still know what x is when we're using the machine. We also have a picture that represents the machine, that represents the values that this machine turns out. So when we're talking about f of -2, we're asking what value comes out when we put -2 in for x. On our graph, left and right represents the x's, don't they? So essentially what we're doing is we're saying x equals -2, what's y in this graph? If x is -2, what's y? That's the question. That's what f of -2 means. If x is -2, what is y? X being -2 is here. Y is, okay, there's a dot right there, isn't there? See that dot? What's the y coordinate of that dot? Yeah. It's 3, isn't it? Yeah. So this actually equals 3. Because this ordered pair right there is -2, 3. The x of that dot right there on the picture that represents the rule, or the machine, okay, is -2. And the y that corresponds to that x of -2 is 3. Or what that machine turns out, the dependent variable, what's turned out by the independent variable of -2, or the x. So where on the graph, where on the picture, what's the y coordinate when x is -5? So we look at our picture, -5. Uh-oh. See an issue there? At x is -5, it's an open circle. That's an issue, isn't it? That it's not actually at -5 because that's an open circle, right? Since it's an open circle, we don't actually get there. So this one is actually undefined. We say undefined because the picture, we haven't defined the rule for x is -5. It just doesn't exist. Does not exist, DNE. If we look at 3 though, f of 3, where is the picture, on the picture, what happens when x is 3? Well, x is 3 is right here, so it's there, and it's there. So what are the values for rule f when x is 3? What are the x values? What are the y values? In this case, if x is 3 from this picture, what's y? Yep. -4 is one of them. Or what's the other number? +4 in this case, right? There's 2, which is weird. Which, if you're thinking it, this is not a function, is it? Because the vertical line hits it more than once at that spot. So it's not a function, no. F of 6. What's y when f is 6? When x is 6? 7, isn't that? Because that's at 6, 7. Right? What's y when x is 6? F of 4, what is it? That ordered pair is 4, 5, so that y is 5, so this is 5. Does it go down? Oh, great question. How about here? F of 4, is that on the picture? It's an open circle. Remember what that means? It's not, doesn't officially get there. Just gets stupid close. Yeah. -7 is going to be -3. But we have a different question. We've reversed the question. What is x when y is 3 now? So you have to reverse the way you're thinking about it. You got to go up to y is 3 and find where that dot is and what is the x. x is -2 in this question.